In calculus 1, we did linear approximation using tangent line. So can you pay attention, please? It's actually pretty interesting. When you had a curve in 2D, we said, you know what? It's very hard for me to find this derivative. It's very hard for me to find exactly answer at this point. So what we did before in calculus 1 called numerical approximation with tangent line, linear approximation, we claim this line is close enough to the curve. So when you keep zooming in, instead of finding this point, we would find point on the tangent line and this called error. And we say, more or less the same, like works well. And if you don't go too far on your neighborhood, called neighborhood, or interval, it actually gets really good, like this and this. So there's a whole proof, maybe you don't remember, that sine, right, is exactly a line at 0. At 0, it's the same as line. So sine and cosine have perfect lines between the hoops and pits. Very interesting idea. That's why the limit was 1. Sine of limit x over x, remember? That goes to 1, but only around 0. Around 0. That was calculus 1 class. Taking this idea to upper dimension, it gives you this. Check it out. Here's a surface. Sometimes it's hard to calculate stuff on a surface. What if I want to have this point or this point? Kind of hard. I find tangent plane instead and zoom in. The more I zoom in, the closer it kisses the surface. That's why this kind of idea of kissing it makes sense. The closer it gets. You just kicked me out like completely to a different chapter. Oh, no, it's here. The more you zoom in, the closer it gets to whatever we need. And then we use that as approximation. And the difference will be called error. Whatever is the distance between the plane and the surface called an error. Very cool idea here. This is what I want to mention. The closer we get, the much more the surface of the tangent plane agree with each other. The surface and the tangent plane becomes very close to each other. So close, we might just use that result because it's easier. Plane is flat. Okay, why it's easy in general? Surface has curves and it has ups and downs. Sometimes it's not continuous. Sometimes surfaces have holes in them, like a socket hole on a table, right? It's kind of hard to work with that. Tangent planes are easy. It's flat. That's why derivative everywhere is the same. That's how it's easy to work with tangent plane and tangent line. And that's why we're pushing it so hard into you. It's really useful in approximation, in numerical approximation. So actually, if you watch the movie Hidden Figures, they use Euler's method first. Euler's method literally uses derivative on every single step to approximate the number. That's exactly what they did. This is what I wanted to mention, and some cool applications of what we learned last time. I want to show you heat equation. So, differential equations class covers equations that involve derivative, right? So, unknown is a derivative. So, it's called ordinary differential equation. But there's another class called partial differential equation. Those are the equations that involve partial derivatives. That's why it's really important to teach partial derivative. For example, Laplace equation, heat equation. The equation that tells you how the heat is moving around and changing uses partial derivative. This heat equations uses also series, which we learn in calculus 2. The heat equation looks like that. What is that? We just learned that. So it's pretty cool. It's called Laplace operator if you square it, and so on. So all of this has lots of applications. Heat equation, wave equations are one of the most popular ones. Wave equations are hard. Not only they're using partial derivative, but they're second order. See, they're squared. It's a second order partial derivative. Those are wave equations. Extremely important if you plan to go to engineering and physics. All of this using partial derivative on every single step and has pretty complicated ideas behind it. So that is pretty cool. Partial derivatives are everywhere. Stokes equations are working with space and black holes and gravity. Let me show you that. So Navier-Stokes equation describe the viscous fluids, substances, blah, 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 and also used in space, Newtonian fluids and so on, pressure, temperature, density. Let me show you the cool animation. So it uses partial derivatives and gradients. That's why I wanted to mention that. So those are extremely popular for everyone who is studying physics. Mostly people who study physics know all of this. I also know it because I was just curious about that. And Einstein field equations, space-time lattice analogy. So all of this, all of those gravitational equations are partial differential equations. So we need to know partial derivatives really well. Oops. Here it is. All these formulas. And finally, this one I think was pretty interesting. I put lots of links for you to search, to check them out in the Wikipedia mostly. But it is beautiful. Of course, if you want to study something that's moving, waves, heats keep changing, densities keep changing. Those are partial derivatives. Hope you was impressed. Thank you for coming to class. Have a good day. Like and subscribe. Yes.